So in this chapter on angular motion, apologize for some of the shadows going on there. With angular motion, we'll start by looking at angular position. Angular position is going to be represented by the variable theta. And the units for it are radians. And I think that will start to make sense, even though you might like degrees better. I've always felt, degrees were better, but I think you'll start to understand why radians are actually better scientifically or in this class. What I want to do here is draw an XY axis. And if you remember from math class, we had quadrants, right? That this was the first quadrant, positive x, positive y values in the first quadrant, negative x, positive y values in the second quadrant, right? And then the third quadrant, both being negative, and then positive x, negative y in the fourth quadrant. All right, and the reason I'm bringing this up is because there was a little bit of the order these went in, right? 1, 2, 3, 4. This direction counterclockwise, right? Is how because this is a clock is 12 here, 1, 2. Right? This is counterclockwise. Okay, I think everybody knows that. But this is the idea that we're gonna sweep out our angles from 3 o'clock in this class. Then when we give something an angular position, we're gonna start here as this having right here at 3 o'clock, this having an angular position of 0 degrees. But we're not going to use 0 degrees, we're going to use radians. So this having an angular position of 0 radians. Or if you went all the way around and made this angle, then it would be once around the circle, which is 360 degrees, but we're using radians, so 2 pi radians, right? So that's kind of what I wanted to start by seeing. So really we have a couple conversion factors here, right? We know that 360 degrees is equal to 2 pi radians, and therefore half that, 180 degrees, would equal pi radians. And you can so that should be fine and should make sense. I wanted to add something else there. All right, I guess I'll come back to it if I need to. So anyways, if I come down to say draw what pi radians looks like, or an angle of 180 degrees. We sweep out from 3 o'clock or from the positive x-axis, right? That this is 180 degrees, and this is equal to pi radians. Okay, so if our angle was instead then half that, we know it would be 90 degrees. But we might want to just quickly know, well, how many radians is that? And so half of pi radians would just be 1/2 pi radians. Or you could just say pi over 2 radians. And this is equal to an angle, right? This right here is equal to an angle of 90 degrees. All right, so yeah. What I was going to say up here was that pi is 3.14, and then therefore 360 degrees is about 6.28 radians. So going around a circle is about a little over 6 radians, 6.28 radians, and so that kind of gives you an idea of, I guess, what a radian is. I think if you calculate what a radian is, I think it's around 57 degrees. It's been a while since I've done it, but I can't remember. So I guess we could find it right now. 1 radian is how many degrees? Well, we would just multiply, right? We just do a conversion. So we know that, say, 2 pi radians is equal to 360. So all we're going to do then is convert that. So I guess we just take 360 divided by 2 pi. And we get 57 point, I don't know if you can see that, 57.3 roughly. So every time you hear a radian, you're thinking 57.3 degrees. So once again, 6.28 of those radians, 6.28 times this will equal 360. All right. So coming back to where we were at here, thinking about this, 180 degrees is equal to pi radians helps when you get stuff like, say, a 30-degree angle, right? And if you get this 30-degree angle, you might say, well, what is this in radians? So what you can do is you can divide this into parts, right? Here's 1, 2, 3 parts, and you can keep going, right? 4, this is roughly, right? 5, 6, right? So if you add up 30, 30, 30, that gets you to 90, 30, 30, 30, that gets you to 180. So you can see that it's in 6 parts gets us to 180. So this is 1/6 pi radians, and that's a convenient way to make that change, right? I was thinking also, well, what if they asked you a question like, say, this angle right here, whoops, and you might say, well, what is this angle? Well, it would be 210, right? 210 degrees. And you'd say, well, how many pi radians is that? Well, that's really just the 7th part of that, right? So we just add another 6. This is 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6. So this would equal 7/6 pi radians. All right, so hopefully that's making sense there. All right, let's get a couple more. If we go back and divide this, say here, into 4 parts, and we think about this angle right here, this angle is half of 90, so this would be 45 degrees. But also, if it's divided in fourths, we can now see this is 1/4, 2/4, right, or a half at 90, 3/4, 4/4, or pi. So this is 1/4 of pi, right? Because this is pi all the way to here. So this would equal 1/4 pi radians is the same as, say, 45 degrees. Okay, good. Let's do one more. Let's get 60 degrees. Hopefully you can see where this is going. So here's 60. This would be 120. This would be 180. So we're going to divide it into 3 chunks. And so you can see that 60 degrees is the same as 1/3 pi radians. You might say, well, couldn't you have just looked back at the last page and and said, well, isn't 60 just 2/6, right? Pi radians. Well, 2/6 is the same as 1/3. So yeah. All right. Good. I think that's about it. Let's move on. So this idea of, apologize for that shadow there. Try and keep this over here. This idea of angular position. And position. You know, they seem very similar, and so they are analogous, right? So we can say that theta is analogous to our variable for position, which is maybe x, right? Or maybe y. But maybe we don't want to give it a direction. So instead of saying x or y, we'll just use the variable s, right? And s could mean any direction. So s will stand for spatial position. Right? Because this could be x or y or z or something along those lines. So the reason this is important is that, say, if we stick with that 30-degree angle roughly, let me go ahead and draw this out. And we have something, say, like this, right? A chunk of a circle. And that's a pretty crummy circle, but you get the idea. And this is theta. And this distance right here is r. And r is, if this is a circle, r is just the radius, right? Well, right here, we'll call this the arc length, and we'll set it equal to s. And r is the radius, and theta is our angle. And what we can see by looking at this is that there's actually a relationship between the three, and that is that the arc length is equal to theta times r. And so this is what's nice about radians right here. Because if our angle is in radians, we can just simply multiply by the radius and get the arc length, right? So that is very nice. It's very easy to use and to find the arc length. Assuming we know the radius, right? So let's look at an example of that. Let's say let's say our angle is instead equal to 360 degrees. So let's say we go all the way around the circle. We said that that would be 2 pi radians. So if we grab our formula, s equals, our arc length equals the angle in radians times the radius, we can go ahead and plug in 2 pi radians right here. And multiply by the radius. and when we do that, what we see is that that this is, s is just equal then in that case to 2 pi times r. And you might say, well that looks familiar. That's actually the formula for what? Well, that's the formula for the circumference, right? And so the formula we've been using in math class all this time is just derived from this relationship. And I guess one thing that you might say, well, what happened to the unit radians? Radians is a little bit like a shadow unit here where it just kind of goes away. And we multiplied by meters, so we are left with 2 pi times some amount of meters because it's a radius, a distance. But but that's why this is such a nice formula, and that's where your circumference formula comes from using this. So now you can start to understand why working with radians is actually a little smoother than working with degrees. All right, let's move on to expand on this idea of angular position. So we just said angular position is represented by the variable theta. And therefore, if we change our angular position, theta f minus theta I, we get angular displacement. And that should ring a bell from before, right, where we had regular displacement being delta x and xf minus xi. Okay, and then if we take that angular displacement then and divide by time, right, this should also look familiar. Change in angular displacement over change in time is equal then to angular velocity. And hopefully, these are, this is ringing a bell, right? Just like up here, this was similar to delta x equals xf minus xi. I'm just running out of room, otherwise I'd write all these down. Well, I guess I can write them up here. Delta x is equal to displacement. We saw before that when we take delta x over t, we get velocity. So here it's no surprise that if we take delta theta over t, we get angular velocity. Okay, so let's keep going, right? What happened last time if we took, say, delta v over t? Well, this should look familiar. It's acceleration. So in this case down here, if we take change in, what's this letter? Hopefully you remember this. This is omega, right? And it's the Greek letter omega. It's lowercase omega. If it was uppercase omega, omega looks like this, which is our symbol for resistance, or the unit of resistance, which is ohms. So it's our symbol for ohms. And this is uppercase omega. So this is also omega. So lowercase, uppercase. All right. Anyways, we're using this lowercase one. And if we have a change in omega divided by a change in time, I don't write the delta there, but I could, is equal to angular acceleration. And you might say, well, what symbol is that? And that one is alpha, another Greek letter. All right, good. So let's go ahead and expand now on this relationship up here. What we can see is that because the units on this are for theta are radians, and because the units on, say, angular velocity are in radians per second, and in angular acceleration, the units are radians per second, right? Also known as radians per second squared. That we can actually draw this relationship of taking an angular idea here, an angular quality, right, and multiplying it by r to get an angular equivalent. So, or I'm sorry, linear equivalent. So what I'm saying is not only is position equal to angular position times r, but velocity is equal to angular velocity times r. Whoops, that should be multiplied by r. Let me just rewrite that. Velocity is equal to angular velocity times r. and acceleration is equal to angular acceleration times r. So this is very convenient, right? To go from the linear quality, right? This is linear, to our rotational quality. We can just take the rotational quality and multiply by r. And this is very nice. So it's nice to use. And it's important that you understand this bridge. I think it's the easiest to remember these three, that you just take the angular quality, multiply by r, and you get the linear quality, right? Or they take the rotational quality, multiply by r, and you get the linear quality. You can also rearrange that. So say you want to find the rotational position, right? So if you know S equals theta times r, then theta equals S over r, right? And so that would be another way to write the same formula. Or if you took V equals omega times r, then omega is equal to V over r. So you can see by dividing by the radius, we can get the angular quality, right? So the last one would be acceleration equals alpha r, and then we're gonna just divide by the radius, right? We're just solving for this, so divide both sides by r, and we get a over r is equal to alpha. All right, so hopefully that's sitting well with you and making sense. You can also keep going with this idea of making having analogs for our K formulas. So you should remember what K here means, kinematic, but the formulas were specific to something, right? And you should remember what that is. They were constant acceleration formulas. So they only apply when the acceleration is constant. So we had things like K1, and where do these come from? They come from calculus, actually. And I'll probably make a video explaining how to derive these with calculus, because I know some of you are taking calculus. K2, K3, just going to use delta x, could be y. But you get the idea, right? And yeah, I was trying to think if we should do K4 as well. K4 probably. It's an average velocity kind of deal, right? You're going to take your two velocities and add them up, and then multiply by time, and that's going to give you delta x. So it's useful to know this one because it's not given to you on the AP test, but it is useful because sometimes it comes in handy. All right. Okay, so my point was going to be that just like you have constant acceleration formulas, you can have constant angular acceleration formulas. So we're now going to have equivalents of these, right? So if you know these, you should know these. So this is going to be omega f equals omega I plus alpha times time. This is going to be delta theta equals omega I times t plus 1/2 alpha t squared. And this next one, K3, is going to be omega f squared equals omega I squared plus 2 alpha delta theta. And then finally, delta theta is equal to omega F plus omega I times T. All right, so there you have it. Okay, let's go ahead and move on. So because we're dealing with things that are angular and that say like spin in a circle, something that has angular speed or angular motion is rotating, right? There's a relationship here with angular velocity and circular motion, right? And I guess I should say there's a relationship between velocity, angular velocity, and circular motion. So specifically, what is that relationship, right? We need to start by remembering two qualities that we had talked about before. One is called frequency. And this is the number of cycles. Cycles is kind of a shadow unit like radians. So that's something to remember there. And it kind of just goes away per 1 second. The units here are hertz. And period, which is capital T, not lowercase. And this is lowercase f. And this is equal to the number of seconds per cycle, per 1 cycle. So units here are just seconds. So something to mention here, because this units is just seconds, I kind of ignored this. This got this special unit hertz, it seemed like, even though it's similar. You can really ignore the cycles here and just think of this as per seconds. So 1 over seconds, or all is a hertz. Or you can think of it as seconds to the -1, right? So they are similar, right? Even though this one seems simpler and this one seems more complicated because it's called hertz, but it's really just 1 over seconds, or seconds to the -1. All right. So I guess we can say about cycles, what is it? Well, it means once around the circle. Or, and in this case, once around the circle. It could be anything. It could be me tapping my pencil, right? And if a cycle is a tap, and I tap at 1 cycle per second, then it's 1 1,000, 2 1,000, 3 1,000, 4 1,000. Or if it's 2 cycles per second, then it would be 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, right? And so you can see where this is going, right? So it's one of something, right? But in this case, it's going to be once around the circle because we're interested in circular motion. But it is a shadow unit. And what I mean by that is it's not really there. Okay. So I think to show you these relationships, I think an example would work really well. So, all right, I'm going to pause it right there. So to look at how frequency and period relate to circular motion, let's take a circle here. And let's say that the circumference is 100 miles. All right, it's just once around the circle is 100 miles. And then, therefore, a cycle, the distance of a cycle, would be 100 miles. And let's go ahead and say that the period or the time it takes to get around the circle, right, or the time it takes for a cycle, let's say that the period is equal to 2 seconds. So it's a fast moving object. But it's going to take 2 seconds to go around once, right? Once around the circle takes a time of 2 seconds. So 1 1,000, 2 1,000, right? And that's 100 miles right there. Okay, so if we know that this distance is 100 miles, and we know the time it took 1 1,000, 2 1,000 to go 100 miles, you can kind of see where this is going, right? That we have a distance and we have a time, so we have a velocity, right? So we're saying then that velocity is equal to the distance around, which is well, it's the circumference, right? 2 pi r divided by the period. So we're saying that the velocity is equal to in this would be our formula, but in our case here would be 100 miles, right, which is 2 pi r because it's the circumference, divided by 2 seconds, which is equal to 50 miles per second. Okay, so we have a formula relating velocity and period. Okay, well, we can do a couple things with that, right? We can remember just offhand that frequency is equal to 1 over the period, or the reciprocal of the period. And we could also say that the period is equal to 1 over frequency. And the reason I bring that up is because if frequency is equal to 1 over the period, and we look back at our formula and say that velocity is 2 pi r over t, this is really 1 over t, or 1 over the period. So really then velocity is equal to 2 pi r times the frequency. Another way to think about this is to think about it like to remember what that once around is a cycle, right? And frequency is equal to the number of cycles per second. And if we say then that if we go back to our example, we remember that the period was 2 seconds, right? So this is a cycle once around, right? And if we go around it, so 1 1,000, 2 1,000, and the number of cycles per second is going to be, well, let's look at, let's count it out, right? 1 1,000, 1 second, we go half of a cycle. So therefore, we can say the number of cycles per second is equal to 0.5 cycles per second, which is also equal to 0.5 hertz, or half a hertz, or 1 over 2 cycles per second, right? Something like that. And the reason I bring that up is because if we just, I'm sorry for the shadows there, if we just think in terms of what a cycle is, right, and did a conversion factor, we have 0.5 cycles per second, we said a cycle is once around a circle, and once around the circle, if we do a conversion here, one cycle is equal to 2 pi times the radius, right? Because it's the circumference. So I cancel off my cycles, and I'm left with the frequency right here times 2 pi r, right? So in our case, this was 100 miles, so 100 miles times 0.5. So pretty much I just took whatever once around the circle is and multiplied it by the frequency, right? So I took f and multiplied it by whatever once around the circle is, and I got 0.5 times, or 0.5 cycles per second times 100 miles, and I get 100 miles then over 1 second, right? Times, I almost forgot my 0.5 times 0.5, right? So I have the frequency, which is right here, multiplied by whatever once around the circle is. So you can kind of see that this is going to give us velocity as well, right? And that's where this comes from there. So just by doing the conversion factor. So really we have two new formulas here. I don't know how new they are, and I apologize once again for the shadows. The light keeps moving in here. And so what I'm saying then is our two new formulas are, well, they're not totally new, but you get the idea, right? That velocity is equal to whatever once around the circle is divided by the period, or we can write it as velocity equals whatever once around the circle is times the frequency. And then we can go ahead and do the same thing angularly speaking. So meaning in terms of angular velocity, we can say, well, if once around the circle in angles is 360 degrees, but we want to use radians, we can say it's 2 pi radians. Then we can say that angular velocity is whatever once around the circle is, which is 2 pi radians, it divided by the period. Or we can say that angular velocity is equal to whatever once around the circle is, 360 degrees, but we're not using degrees, we're using radians, so 2 pi radians times the frequency. So now we have a new formula for angular velocity. Well, two of them really. This one is probably the one we'll use more. And a new formula for, or two new formulas for regular velocity. So I just want you to understand where these formulas are coming from, right? When you see, you can just take whatever once around a circle is, multiply it by the frequency and get that type of velocity. So you can... I'll go ahead and write that down. You can take whatever once around the circle. And you could also, instead of saying multiply by frequency, you could have put in there divide by the period. And so yeah, so I want you to recognize, because these formulas are going to show up and I want you to know where they came from. All right, that's it.